Hello students, welcome to the video lecture series on Chemical Engineering Thermodynamics 2. I am Jamin Pandya, Assistant Professor in Chemical Engineering Department of LJIET Institute of Engineering and Technology. So let's continue with the chapter number 3, which is a chemical reaction equilibria. So in this lecture we are going to discuss about the application of equilibrium criteria to chemical reaction. Then we are going to discuss about the equilibrium constant, which denote by K. So let's discuss about application of equilibrium criteria to chemical reaction. A criteria for thermal equilibrium is a simple. For the thermal equilibrium, there will be a temperature is a constant. For the mechanical equilibrium, there will be a pressure is a constant. But for chemical reaction equilibrium and for the chemical reaction, there is no same criteria. There is an additional criteria. For example, if a liquid is converting into the vapor and vapor is converted into the liquid, then the mass flow rate of this liquid to vapor and vapor to liquid will be the same for the chemical reaction equilibrium. Okay. To understand this, let's consider the fundamental property relation for the chemical potential that can be given by dGt is equal to VdP minus SdT plus summation of mu I dni. This is a fundamental property relation for chemical potential, which we already derived in chapter number 2. So at constant temperature, this term becomes cancelled. At constant pressure, this term becomes cancelled. So can say that dGt at constant temperature and pressure is equal to summation of mu I dni. Now we already derived dni is equal to Vi into d epsilon in previous lecture. Okay, so I am just replacing this dni with Vi d epsilon. So if I am going to replace this dni with Vi d epsilon, then equation becomes dGt at constant temperature and pressure is equal to Vi mu I into Vi into d epsilon. To understand and summation of this all term. To understand this more clearly, let's consider a simple reaction A gives B. Now, I am going to write the equation for this reaction. So it becomes dGt is equal to mu A VA d epsilon plus mu B VB d epsilon. Okay, so what is value of VA and VB? What is meaning of VA and VE? VA, which means stoichiometric number of component A, and VB, which is a stoichiometric number of component B. So what is stoichiometric number for this A? Stoichiometric number for the reactant is always negative, so this is -1 and this is +1 and this is +1. Now putting value of this stoichiometric number, we will get dGt is equal to mu B d epsilon minus mu A d epsilon. Putting the value of this -1, so it becomes minus mu A d epsilon. Putting value of VB, it becomes mu B d epsilon. Now taking this d epsilon common, it becomes mu B minus mu A into d epsilon. So I can write that del GT upon del epsilon at constant temperature and pressure, the equation becomes mu B minus mu A. So this is the equation for criteria for the chemical reaction. So let's again write this equation. So it becomes del GT upon del epsilon at constant temperature and pressure is equal to mu B minus mu A. So this is the chemical potential for component B and this is chemical potential for component A. Component A, which is our reactant, where component B, which is our product. So for forward direction reaction, the chemical potential, or can say that Gibbs free energy, that can be given by del GT upon del epsilon constant temperature pressure, which is less than 0, for when the chemical potential of particular component A or the reactant is larger than product. So if A is larger than B, then can say that value of this is a less than 0. If this value is higher, then if this value is higher than this, then this value will be a less than 0. If del GT upon del epsilon at constant pressure, if the value of A is less than mu B, then can say that del GT upon del epsilon will be greater than 0. Okay, but if both value are same, which means chemical equilibrium, then can say that del GT upon del epsilon is equal to 0 when mu A is equal to mu B. So can say that when chemical potential is equal for each component, then Gibbs free energy is the minimum for particular component. So when the Gibbs free energy is minimum, the ratio of del GT upon del epsilon becomes 0. So at this point, Gibbs free energy is the minimum. Well, the Gibbs free energy is minimum when value of or can say that chemical potential of component A and chemical potential of component B are same, or also can say that chemical potential of reactant and chemical potential of product are same. At that time, the Gibbs free energy is the minimum, and value of that Gibbs free energy, or can say that differentiation of that Gibbs free energy in term of extent of reaction is 0 at equilibrium. So this is how we can prove the Gibbs free energy is the minimum at the equilibrium. Now let's discuss about the equilibrium constant. The equilibrium constant, which denote by capital K. Okay, so equilibrium constant, which denote by capital K for reaction, defined in term of the fugacity or in term of the activity. To understand this, let's consider the reaction small a plus a into small b into b gives small c into c plus small d into d. Okay, so this small a, b, c and d is a stoichiometric number where capital A, capital B, capital C, capital D are chemical compound. Okay, so equilibrium constant for this reaction that are defined by K is equal to Ka. So here we are going to write the equilibrium constant in term of the activity. So it becomes activity of a particular this product, which is a C, into activity of particular product D. So and power of C and power of D. Okay, so this becomes like this: A into A of small a and activity of component B, power of stoichiometric number of that particular component B. So it's defined by this, and which known as a capital pi into Ai into Vi. So what is meaning of this capital pi? Okay, capital. We are let's first understand what is meaning of summation Ai. If I am going to say summation of Ai, which means A1 plus A2 plus A3 and so on to Ai. Okay, so if I am going to say capital pi into Ai, so it becomes A1 into A2 into A3 into A4 and so on to Ai. So in sigma we are going to summation of all the component, where if I am going to use capital pi, which means multiplication of all component. Okay, so here this is our reactant. Okay, that's why if we are going to write Ai is equal to, let's this write Ai for this reaction, then can say that activity of particular component A, power of Vi stoichiometric number for this A, which is small a, but for reactant this becomes minus A. So This becomes minus A into activity of component B. Stoichiometric number for component B is a small b, but it is reaction, so it becomes minus B into activity of component C. So this becomes our activity for component C, power of stoichiometric number. Stoichiometric number for this is C into activity of component D, and stoichiometric number for D is a small d, and these both are positive because chemical potential is a positive for the product and negative for the reactant. So this is minus, so I can write this whole term like in this equation. There will be a minus, so I can write in bottom. That's why this equation becomes like this. Okay, so this is the chemical potential in term of the activity. Now we know that activity definition of activity that can be given by AI is equal to Fi bar upon Fi naught. Activity is a relative fugacity in a solution upon fugacity at standard state. So if I am going to put the value of this AI in this previous equation, then the chemical potential becomes K is equal to capital pi of Fi bar upon Fi naught whole raised to stoichiometric number. So it becomes our equilibrium constant. Okay, so this is how we can define the equilibrium constant. Equilibrium constant that can be given by pi of AI whole raised to Vi. Now we know that activity that can be given by relative fugacity, so can say that pi of Fi bar upon Fi naught whole raised to Vi. So this is known as a equilibrium constant in term of the activity and in term of the fugacity. So this is all about today's lecture. In next lecture we are going to discuss about the standard Gibbs free energy change, or we are going to prove del G naught is equal to minus RT ln K, which is the most important question in this chemical engineering thermodynamics too. So this is all about today's lecture. I am completing my lecture here. Thank you.